Okay. In this video, I'm going to introduce a very powerful tool. It's called the central limit theorem, and it may arguably be the most important statistical tool out there, maybe even all of mathematics. And maybe I'm going a little bit too far here, but the central limit theorem is the basis for allowing us to use the Gaussian distribution on many processes. And so for us in the measurement world, where we're trying to figure out what the true value is through measurement, it is critical for us to understand the central limit theorem. And obviously, we won't be applying the central limit theorem in a very direct way, but in an indirect way, almost every single time we do an uncertainty analysis and we are calculating the uncertainty related to our precision components, we are applying the central limit theorem. So this is paramount. This is a very important topic to cover. What is it? Why is it useful? That's what we're going to talk about right now. So here's some language, and I know it's a lot, but I will kind of summarize what's going on here. The central limit theorem allows us to estimate the probable difference between the average value of a small sample and the true mean of a larger population. So if we think about our population and our sample, and we pulled out the handful of marbles from the bag of marbles, and we're like, does the mean and standard deviation of this smaller sample represent the mean and standard deviation of the overall population? The central limit theorem allows us to make that connection. So the probable difference or confidence interval provides an estimate of the precision uncertainty associated with our measurement sample. That's just, I don't know if I can emphasize this enough, but that is mind-blowing that we are going to be able to make that assumption of the sample represents the population. In probability theory, central limit theorem establishes that in many situations for independent and identically distributed random variables, the sample distribution for the standardized sample mean tends toward the standard normal distribution, even if the original variables themselves are not normally distributed. Oh man, that's so much language there. This last sentence kind of summarizes it. This theorem applies for very large samples, even if the distribution of the underlying population is not Gaussian. So we're out there in the real world measuring something. Maybe we're a fundamental scientist and we're measuring something that no one's ever measured before. Or maybe we are in a manufacturing plant and we're taking quality control samples off of the production line. Maybe the samples or the distribution that we have is not Gaussian. How are we going to come up with that precision uncertainty? Well, using the central limit theorem, we can actually take samples of the population, and then even if they're not distributed like a Gaussian distribution, we can have them be represented by a Gaussian distribution using the central limit theorem. Amazing. So I want you to watch these two videos. They're from the Khan Academy, and I think they are, I don't know that I would be able to reproduce them in a better way, a more meaningful way than what he has done. And so I want you to watch these two videos. Do not skip these videos. Don't fast forward them. Do watch them and do your best to understand all of the concepts that he's talking about, because the central limit theorem is very critical to the understanding of our precision uncertainty analysis that we're going to be doing throughout the entire class and hopefully throughout your career. I will argue that instrumentation and measurements is one of the most applicable classes that anyone can take as an undergraduate for mechanical engineering. And this right here is one of the core concepts that you should know. So once you're done with that, this slide is going to make a lot more sense. But a few key concepts when we're watching this and we're thinking through is that if we have something that is not Gaussian, so this distribution shape can be discrete, it can be shaped in all kinds of different ways. And if we take enough samples, so we take the number of samples each time, so if we have a bag of marbles, we pull out, say 5 marbles each time, and then we pull out 30 sets of 5, Then we can look at the mean and standard deviation of those sets and then compile them into a new distribution. And that new distribution is going to be Gaussian. Isn't that crazy? And so the higher the number of samples, so instead of taking 5 out, maybe we take 30 out, and we take those 30 out 30 times. The more and more you do that, the higher number of samples and the more times you take those samples, the more it's going to be Gaussian. And so those are two very important concepts to keep in mind as you're going through this. I think the last slide here that I wanted to share is pretty much just a summary of what we've been talking about here. But this equation right here, 3.17, this equation is one that we use all of the time. And so these equations right here, we're using these to represent the overall population. And so back to our confidence interval, we've got the mean plus or minus some uncertainty. So this right here is the uncertainty related to a sample that represents the overall population.